Hello viewers, you are already familiar with how microprocessor operates as a programmable sequential and von Neumann machine. Today I would discuss about the generic architecture of a microprocessor. Then I would discuss about a specific microprocessor Intel 8085A. The generic architecture containing various functional components are shown in the schematic diagram. The major components are registers, the arithmetic and logic unit abbreviated as ALU, the timing and control unit, the internal bus and external bus, the power supplies and the internal power distributions. The line diagram shows the classification of the registers. Primarily, the two major types are the accessible registers, which the programmer can access, and the inaccessible registers, which are non-accessible to the programmers. The accessible registers, in turn, can be grouped into general purpose registers and special purpose registers. General purpose registers store temporary data and address. Its main characteristics are: width of these registers are equal to the word length of the processor. Registers may be paired for storing address. Accumulator is one essential general purpose register. All microprocessors must have at least one accumulator. The main functions of accumulator are: it serves both as source and destination register and provides one input to ALU. Except in certain cases, the data movement from or to I/O devices always takes place through the accumulator. Besides general purpose registers, there are other accessible registers called the special purpose registers, abbreviated as SPR. SPRs are used as memory pointer and their width is equal to the address bus. The SPRs are broadly divided into program counter, index register, and stack pointer. Program counter, that is PC, is a special purpose register that keeps track of the instruction, and after completion of each instruction, it indicates the address of the next instruction to be fetched by the processor. The PC automatically increments by one or more depending upon the length of the instruction, so that it always points to the next instruction to be fetched. Sometimes it becomes necessary to branch out from sequentially stored instruction to a memory store, where a set of instructions are stored. After executing those instructions, the processor resumes the execution where it left earlier. In such situations, it is required to save the return address and possibly status of some of the general purpose registers before branching. The stack and stack pointer is used to save this information. The contents of the stack are the information to be saved, and the stack pointer points to the location where the information is stored. The stack is an array of registers and may be organized either as first in, first out FIFO or as a last in, first out LIFO manner. Let us see a video clipping of a real-life example of a FIFO stack. We have seen that the record placed first is played first. Let us now see the video clipping of a real-life example of a LIFO stack. We have seen that the last dish is being used first out of the stack of dishes. In computer, usually LIFO stack is used. The two possible operations of a stack are push and pop. Pushing down can be thought of as putting a new item on top, and popping up as moving the top item out. You can see that before a push or pop operation, 3 bytes, namely 76, EA and 50, are placed in the stack in order. The data 76 is on the top of the stack. The stack pointer points to the top of the stack. The content of stack pointer is the memory address of top of stack, which is EF52. As a new 1 byte data A5 is entered or pushed into the stack, top of the stack assumes a new position, and this is indicated by decrementing the content of the stack pointer by 1. Now, content of stack pointer becomes EF51, and stack pointer points to the data A5. Similarly, if 1 byte data is removed or popped out, the top of the stack assumes a new position, and this is indicated by incrementing the content of the stack pointer by 1. Now, content of stack pointer becomes EF53, and stack pointer points to the data EA. We have learned the pop and push operation of LIFO stack as implemented in computers. Also, we noticed that the width of the stack pointer is equal to the width of the address bus. In some microprocessors, there is another type of special purpose register known as index register. The index register is used to facilitate a special kind of addressing mode known as indexed addressing. This is useful for array processing and fetching data from contiguous memory locations. Let's see some video clippings. Flag is waved to start the sprint. This is an event that takes place depending on the condition of the flag. Similarly, in microprocessors, besides the memory pointers and the general purpose registers, there is a set of 1-bit flip-flops known as status flags or condition code bits. These status flags are set or reset to reflect the results of arithmetic and logical operations. Most of these flags can be sensed by the programmer using various instructions, and actions may be taken depending on their status. Microprocessors have some registers not accessible to the programmers. They are instruction register and temporary registers. Width of these registers are equal to the width of the microprocessor data bus. You have learned that instruction consists of two parts: opcode and operand. The opcode indicates the type of instruction to be executed, that is, add, subtract, etc. And operand provides the data needed to execute the instruction. The instructions may be of variable length. However, opcode part, which is of fixed length, is fetched from the memory and stored in a temporary register known as instruction register. It then goes to the instruction decoder, which directs the timing and control unit to generate proper signals for execution of the instruction. These registers are used by the ALU and the control section for temporary storage of data at various stages of instruction execution. This is how the whole structure of registers in a microprocessor looks like. Every microprocessor must have at least one ALU. It performs the specific arithmetic and logical operations on data present in its two input. ALU has two inputs and one output. One input to it always comes from the accumulator, and the result of the operation is also stored in the accumulator. The timing and control unit acts as the heart of the microprocessor. It issues appropriate signals to units internal and external to the CPU for coordinating and controlling the activities of the microprocessor. It is similar to the action of a conductor in an orchestra. Microprocessors are typically synchronous sequential circuits. Each activity is synchronized on the basis of a clock signal. Let's take one example. The drum beating provides the required timing to the cadets, and its action is similar to a clock in the microprocessor. In some microprocessors, the clock unit is inbuilt, while in others, the clock pulse is generated externally. In either case, the clock frequency is generated using an external crystal or some alternative circuits. The microprocessor allows certain control input signals. The most commonly available input signals are reset, interrupt, and bus control signal. Reset input is activated to initialize some of the internal registers, especially the program counter and status flags, to some predetermined values. Interrupt input is used to suspend the execution of the program after the current instruction cycle and to jump to a program segment known as interrupt service routine. The CPU again resumes the execution of the suspended work. Let's now see a similar situation. Here, the person's reading is being interrupted by phone call. He attends the phone call after keeping a bookmark. The attending of the phone call is similar to service routine execution. Person again resumes his reading by referring to the bookmark. In certain situations, such as direct memory access, microprocessor relinquishes the control of address, data, and control lines to some external devices by the use of bus control signal. Control output signals are generated by microprocessor for the ease of external interfacing. The most commonly available signals are read-write bar timing signal for interfacing memory and I/O with the microprocessor, and status signal for providing information about the nature of the instruction the microprocessor is executing. Most common microprocessors have address data bus organized architecture. Such an architecture communicates with external memory and I/O devices through unidirectional bus which address a particular memory or I/O location, and a bidirectional data bus for movement of data from and to the microprocessor. Control lines provide information about direction of data movement to the microprocessor as well as to the external devices. In addition, there are some external control input-output signals. The internal address and data bus are suitably buffered to provide the external buffered address and data bus. Microprocessors usually require a single plus 5 volt supply line and a ground line. These are distributed throughout the PCB. Let's now consider a specific microprocessor, Intel 8085A. It is an 8-bit microprocessor with 16-bit address and 8-bit data bus multiplexed in 16 pins. 8085A has one 8-bit accumulator designated as A register, 6 8-bit general purpose registers designated as B, C, D, E, H, and L. They are arranged in pairs so that they may be addressed either singly for 8-bit operation or in pairs such as BC, D, or HL for 16-bit operation. Registers H and L are also used for referencing memory. There is one 16-bit program counter, one 16-bit stack pointer, and one flag register. There are 5 1-bit flag flip-flops which form the content of the flag register. Flags are carry, 0, parity, sign, and auxiliary carry. Accumulator and flag register form a 16-bit register pair known as program status word, abbreviated as PSW. There is one 8-bit ALU with additional capability of converting accumulator's content to BCD form. 8085A microprocessor also has 3 temporary registers for ALU and internal data manipulation. In 8085A, stack operation push and pop uses 2 bytes, and so the stack pointer is incremented or decremented by 2 after each stack operation. It has an 8-bit instruction register and decoder. Clock circuit is inbuilt with an external crystal for generation of clock pulse. It has 8 control input signals, of which 5 are for interrupt signals, and the other 3 are for reset in bar, hold, and ready. 8085A has 9 control output signals, of which 2 are for status signals and 1 each for reset out, hold acknowledge, read bar, write bar, IOM bar, address latch enable, abbreviated as ALE, and INTA bar. It has also one inbuilt serial input data, abbreviated as SID, and one serial output data, abbreviated as SOD port. External data and address bus are buffered. We have already seen that 8085A microprocessor uses multiplexed address data bus. The address is split between higher 8-bit address bus and the lower 8-bit address data bus. For a specified period, lower 8-bit address data bus provide the lower order 8-bit address, and then it acts as 8-bit data bus. The timing is provided by a control signal known as address latch enable. Friends, I have explained to you the generic architecture of microprocessors and the architecture of an Intel 8085A microprocessor. But I may remind you that this is only a gateway to the vast domain of microprocessors, which you will master only when you work with it.